If we examine any phenomenon related to an electrostatic field in the presence of dielectrics, it is useful to distinguish between bound and extraneous or free electric charges. Bound charges are the charges in the atoms and molecules of dielectrics, as well as the ionic charges in dielectrics with an ionic lattice crystal. As discussed earlier, these charges are displaced only slightly from their equilibrium position under the influence of an electric field, and they cannot leave the atoms or the molecules containing them and move throughout the material. Consequently, bound charges represent the internal dipoles induced in the polarization of dielectrics contributing to the overall polarization charge density, but they do not produce a conduction current of charges in the material. Apart from bound charges, all other charges are called extraneous or free charges, that is, charges that are not attached to specific atoms or molecules, allowing them to move freely. Extraneous charges are, for example, the charges of the conduction electrons of metals, the charges of ions and electrolytes and gases, and the excess charges transferred to conductive or non-conductive bodies. All these types of charge move in response to an external electric field, and they are responsible for electrical conductivity, and the electric current in a conductive material is produced by these moving free charges. In a dielectric, the electric field strength is determined by the superposition of the field strength E produced by extraneous charges and the field strength EB due to bound charges. The resulting field strength EM is called microscopic or real field strength. The microscopic field strength varies in a great extent within the distances between atoms or molecules. However, this variation cannot be observed in macroscopic scale, so the electric field is characterized by the value of the microscopic electric field averaged over an infinitesimally small volume. Then the electric field E is the superposition of the averaged electric fields due to extraneous charges and bound charges. In the absence of any dielectric that is in a vacuum, the macroscopic electric field strength is reduced to the average of the free charges. The volume charge density ρ describing the spatial distribution of free charges is the source of such an electric field in the fundamental equation, stating that the charge density ρ divided by the vacuum permittivity is equal to the divergence of the electric field E. We also note that if the free charges represented by the charge density ρ are constant in time, then the electric field given by this equation has the same properties as an electrostatic field in a vacuum. As already stated in the discussion on the polarization of insulating materials, we need incorporate its effects in vacuum electrostatics to provide a general description of electrostatic fields in dielectrics. This will be achieved by introducing a quantity called electric displacement representing the electric field due to free charges and excluding bound charges. In order to do so, let us consider an experiment where we suppose that the space between the plates of a charged parallel plate capacitor is filled with an isotropic insulating material that has the relative dielectric constant epsilon r. We already saw that the capacitor with the electric charges plus Q and minus Q on its plates has a uniform electric field E between the plates, and the polarization charges plus Q and minus Q induced on the boundary surfaces of the dielectric adjacent with the plates produce a uniform electric field E prime pointing in the opposite direction. We also established that the uniform vector field P describes the polarization of the isotropic dielectric pointing from the negative polarization charges to the positive ones. As a Gaussian surface S, we can consider a box with the cross-section indicated by the yellow line in the figure enclosing the positive charge Q on the plate of the capacitor and the negative charge Q' on the boundary of the dielectric. By applying Gauss's law for this closed surface, we can find that the surface integral of the electric field over the surface S is equal to the total charge inside the surface given by the sum of Q and negative Q' over the vacuum permittivity epsilon naught. We already described the polarization charges plus and minus Q' by the product of the charge Q and 1 minus 1 over the relative permittivity epsilon r of the dielectric. If we substitute this expression in the right-hand side of the equation, then the latter can be written as Q over epsilon naught times epsilon r. According to this result, the form of Gauss law derived for a vacuum can also be applied to a dielectric with the modification that the charge Q is replaced by Q minus Q', that is Q over epsilon r, due to the fact that the field strength E is epsilon r times smaller in the dielectric than in a vacuum. Or with the modification where we write epsilon r times E instead of the field strength E prevailing in the dielectric. Now we consider the general case of the non-uniform polarization of a dielectric. Then the equation following from the application of Gauss's law states that the surface integral of the electric field E over any closed surface is equal to the sum of the free charges Q and the polarization or bound charges Qp within that surface, over the vacuum permittivity epsilon naught. We already showed that the polarization charge Q induced in a given volume of a dielectric is equal to the negative surface integral of the polarization P over the boundary surface of the volume. If the Gaussian surface encloses this volume, then we can substitute this surface integral into Gauss's law, and we obtain the equation stating that the surface integral of the sum of the vacuum dielectric constant epsilon naught times the electric field strength E and the polarization P over the Gaussian surface, is equal to the total amount of the free charges Q within the surface. Now we introduce the vector field of the electric displacement D of an insulating material by the sum of vacuum permittivity epsilon naught times the electric field strength E in the dielectric, and the polarization P of the dielectric. This quantity is also called electric flux density, and it has the same SI unit as the polarization, that is Coulomb per square meter. As its definition shows, electric displacement is called the displacement field because it differs from the product of the vacuum permittivity and the electric field strength due to the displacement of the bound charges in atoms and molecules that make up materials when they are polarized in an electric field. In other words, electric displacement separating free charges from bound charges measures the free charge per unit area that is displaced across any material when an electric field is applied, as the name electric flux density indicates. For electric displacement, we can apply the so-called hydraulic analogy between a charged capacitor with a dielectric between its plates, and a pipe with a membrane that is completely filled with water. In this analogy, the electric field E between the plates with positive and negative charges is equivalent to the pressure gradient in the water, or the difference delta P between the pressures P1 and P2 of the two chambers in the pipe separated by the membrane. The electric polarization P in the dielectrics due to the electric field E representing the displacement of bound charges is equivalent to the actual deformation of the membrane stretched by the incompressible fluid. The latter means that a given amount of water is displaced in both sides of the membrane, and the volume of the displaced liquid is proportional to the difference delta P in the pressure, as in the case of the capacitor where the polarization and the electric displacement are proportional to the potential difference between the plates. The hydraulic analogy between electricity and pipes and chambers filled with water is a more general method, and as we will see, it is also applied to study electric current produced by moving charge carriers and conductors. Hence, electric circuits can be modeled by hydraulic circuits. By introducing the electric displacement field D, we can substitute its definition into Gauss's law derived for polarized dielectrics, and write Gauss's law for the general case in a simple form stating that the surface integral of the electric displacement D over an arbitrary closed surface is equal to the free charge Q enclosed within that surface. Then Gauss's law for dielectrics tells us that the displacement flux passing through an arbitrary closed surface is equal to the free charges or their algebraic sum within the surface. This equation indicates that the force lines of the displacement field originate and end only on free charges, and the electric displacement therefore depends only on free charges and not bound charges. As a result, we can ignore the specific properties of dielectric materials with polarization charges, which simplifies the calculations. In the specific case of a polarized insulating material between the plates of a capacitor with a constant charge, the electric displacement is independent of the nature of the dielectric. The situation is different for a capacitor with a constant voltage, where the amount of free charges on its plates depend on the dielectric material inserted into the space between the plates. Because the free charges per unit area on the plates can be different for different dielectrics, besides the constant voltage applied to the capacitor, the properties of the insulating material also determines the electric displacement field between the plates. In the figure, the insulating material does not fill the whole space between the plates of the charged capacitor, and there are gaps between its plates and the adjacent boundary surfaces of the dielectric. The density of the force lines of the electric field indicates that the electric field strength E naught due to the free charges plus and minus Q on the plates is greater in the gaps than in the insulating material, as already shown. In a vacuum or in the air filling the gaps, the polarization vector P vanishes and the displacement D is simply given by epsilon naught times the field strength E naught. If the dielectric is isotropic and the electric field is uniform in the dielectric, then the electric field strength E, the electric displacement D, and the polarization P point in the same direction, and they have constant magnitudes. The vector field D is the same both in the gap and the insulating material, since the presence of the polarization field P in the dielectric reduces the field strength from E naught to E there. The fact that the displacement field is only related to free charges can also be illustrated by the force lines of the field starting from the positive free charges Q and terminating at the negative ones on the plates of the capacitor. Here the polarization charges at the boundary of the dielectric have no any role whatsoever. Conversely, the polarization field P is only related to the bound charges, and its force lines originate at the positive polarization charges Q' and end at the negative ones. Only the electric field E have a direct relation to both types of charges, where the difference in the density of its force line indicates the presence of these charges, as seen in the first figure. We can express the total amount of free charges Q within any volume V by the volume integral of the volume charge density ρ of the free charges over the volume V, and apply Gauss's divergence theorem for the integral form of Gauss's law. Then we immediately obtain the differential form of Gauss's law stating that the divergence of the electric displacement vector d at any point is equal to the volume charge density ρ of the free charges at that point. This formula indicates that free charges are the direct sources of the electric displacement field, that is, the electric flux density at any point is given by the density of the free charges at that point. Again, the presence of bound charges in the dielectric does not play any role as a direct source for the displacement. However, polarization influences displacement indirectly, and it can be shown that the spatial variation in the polarization field has a contribution to the displacement field in dielectrics as well. In fact, the integral or differential form of Gauss's law describing the relation between electric displacement and free charges constitutes one of the fundamental equations of electrodynamics called Maxwell equations. As already explained, the electric field lines always originate and end on free or polarized charges. Hence, there are no closed electric field lines and the field is non-rotational even within dielectrics. Consequently, the other fundamental law of electrostatics derived for a vacuum also applies to dielectrics, according to which the line integral of the field strength E along any closed curve is equal to 0. This means that the electrostatic field E is curl-free not only in a vacuum but also in dielectrics, which constitutes another Maxwell equation in electrostatics. If we calculate the curl of the displacement field D for a dielectric in an electrostatic field and apply the non-rotational property of the later, then we can see that it is equal to the curl of the polarization P in the dielectric. This result indicates that the spatial variation in polarization has an influence on the displacement field, and as already stated it is due to the non-curl-free part in the Helmholtz decomposition of the vector field of polarization. If we want to illustrate a general situation in electrostatic, then we can consider an arbitrary set of conducting bodies with free electric charge described by the volume charge density ρ producing the electric field E or the displacement field D, and some dielectric material placed in this field with the polarization described by the vector field P where the surface and volume distribution of the polarization charges are given by the densities sigma P and ρ P. We note that in the case of conductors free charges can only be found on the boundary surfaces of the bodies and the volume charge density ρ is the general form of their singular surface charge distribution. Then the general form of the fundamental equations in electrostatic consists of the two Maxwell equations stating that the divergence of the electric displacement D is equal to the volume charge density ρ of the free charges, and that the electric field E is always curl-free. Here the relation between the vector fields E and D is described by the equation stating that the displacement vector D is equal to the product of the vacuum permittivity epsilon naught and the electric field strength vector E, plus the polarization vector P. We need to supplement the two Maxwell equations with the other three equations describing the polarization field, where the first equation states that the surface charge density sigma P of the polarization charges is equal to the dot product of the polarization vector P and the surface normal n of any polarized dielectric pointing outward from its boundary surface. The second equation states that the volume charge density ρ P is given by the negative divergence of the polarization vector field P, and the third equation states that the polarization field P must vanish outside any dielectric. This set of equations contains three scalar fields such as the volume charge density ρ of free electric charges, the volume charge density ρ P of polarization or bound charges, and the surface charge density sigma P of polarization charges. We note that the later can be included as a singular charge density distribution in the volume charge density of polarization charges, as the volume charge density of free charges includes the distribution of free charges over the boundary surfaces of conductors. Although these scalar fields are the sources of the vector fields appearing in the Maxwell equations, the vector fields also have influence of the spatial and surface distribution of free and polarization charges. These equations contain only two vector fields that can be considered as independent quantities, the electric field strength E, and the polarization field P or alternatively the displacement field D. This shows that while we only need the vector of the electric field strength E to describe the electrostatic field in a vacuum, it is also necessary to know the vector of the polarization P or the electric displacement D to describe electric fields in matter, and the two fundamental equations must be supplemented with another vector equation. In order to provide that vector equation, we basically need to determine the polarization vector from the properties of the polarized dielectric material. If the atomic structure of matter is known, then in principle it is possible to calculate the displacement of electrons and nuclei when an insulating material is placed into an electric field. Obviously, in this way we obtain different and very complicated descriptions for the polarization depending on the specific cases. There is no universal relationship between polarization and electric field that applies to all materials, and we have to rely on experiments to determine the missing equation mentioned above. For a significant part of dielectrics and a wide range of phenomena, experiments show that the relationship between the vectors of polarization and electric field strength is linear and homogeneous. Such a law can be explained by the fact that the macroscopic field strength is usually very small compared to the internal microscopic field strength of atoms and molecules. If the medium is isotropic, then the vectors of the polarization in the medium and the electric field applied to the medium are unidirectional, and the relationship between them is described by the equation stating that the polarization P is equal to a dimensionless constant chi times the vacuum permittivity epsilon naught times the electric field strength E. Chi is called the electric susceptibility of the medium, and it is the quantitative measure of the extent to which an electric field applied to a dielectric material causes polarization. This table shows the electric susceptibility and the relative permittivity for a vacuum and some substances from air with the lowest values to water with the highest ones. Here we can see that these values span several orders of magnitude, indicating their strong dependence on the atomic or molecular structures of different substances. We define the electric displacement vector D by the sum of epsilon naught times the vector E and the vector P. By substituting the relation between the vectors P and E into this equation, we can write the vector D as epsilon naught times 1 plus chi E times the vector E. We already saw that Gauss's law for isotropic dielectric states that the surface integral of the electric field E over a closed surface is equal to the free charge Q enclosed by the surface over the product of the vacuum permittivity epsilon naught and the relative permittivity epsilon R of the dielectric within the closed surface. It was also shown that Gauss's law can be written in the form stating that the surface integral of the electric displacement D over a closed surface gives the free charge Q enclosed by that surface. If we substitute the expression obtained for the electric displacement D into the second integral equation and compare the result with the first equation, then we find that the electric displacement D of linear dielectrics, in which the polarization is directly proportional to the electric field, is given by the vacuum permittivity epsilon naught times the relative permittivity epsilon R of the dielectric, times the electric field strength E. As a result, we can express the relative permittivity epsilon R as 1 plus the electric susceptibility chi E of the dielectric. This relationship between epsilon R and chi E R can be seen in the table as well. Maxwell equations in electrostatic must be supplemented with any of the vector equations derived here for either the polarization or the displacement field describing a material's response to an electric field applied on a body made of the given material. We established that isotropic dielectric materials have a linear response for external electric fields, that is, the relationship between the displacement field in a dielectric is directly proportional to the electric field applied to the medium. However, there are also anisotropic materials such as crystals, layered substances and structural or composite materials, where the relationship between polarization and electric field is more complicated and its mathematical expression must be generalized. In a more general description for polarization in anisotropic dielectrics, each component of the polarization vector is given by the linear combination of the components of the electric field strength. Then in a Cartesian coordinate system, the x component of the polarization vector P can be written as the vacuum permittivity epsilon naught times the sum of the constant chi sub x times the x component of the electric field strength E, the constant chi sub xy times the y component of the electric field strength E, and the constant chi sub xz times the z component of the electric field strength E. We have a similar equation for the y component of the polarization P with the constant coefficients chi sub yx, chi sub yy and chi sub zy, whereas the constant coefficients in the equation for the z component of the vector P are denoted by chi sub zx, chi sub zy, and chi sub zz. Hence, we can write the ith component of the polarization P, where the index I denotes the coordinates x, y, and z, as the vacuum permittivity epsilon naught times the sum of chi sub ig times the jth component of the electric field strength for the index j running through the coordinates x, y, and z. As an example for anisotropic dielectrics, we show the toy model of the unit cell of the alpha quartz crystal made up of silicon and oxygen atoms. The model illustrates the internal structure created by the chemical bonds between the atoms, where the physical properties of the crystal differ depending on the direction of the measurement. If the unit vectors Ex, Ey, and Ez are oriented along the faces of the unit cell as seen in the figure, then the polarization vector and the electric field strength can be expanded in this basis, and we obtain the component equations shown in the left-hand side. These equations represent a single vector equation with a matrix vector multiplication, where the polarization vector P is equal to epsilon naught times a matrix with the elements of the coefficients chi sub ij, times the vector of the electric field strength E. In fact, the elements in the matrix can be interpreted as the components of a second-rank tensor, and we can introduce the electric susceptibility tensor chi-e as a linear map transforming vectors into vectors, where its scalar multiplication with the vacuum permittivity maps the electric field strength E onto the polarization vector P at any point of a dielectric. Then the evaluation of this second-rank tensor in a specific Cartesian basis gives the elements chi sub ij of the matrix representation of the tensor in that basis. Because the form of the components equations is invariant under basis transformations, the matrix vector product in the vector equation can be interpreted as the contraction of a second-rank tensor with a vector. In other words, the polarization vector P in an anisotropic material is given by the vacuum permittivity epsilon naught times the contraction of the electric susceptibility tensor chi-e of the material with the vector of the electric field strength E applied to the material. Based on this interpretation, we can also generalize the relative permittivity of an anisotropic dielectric, and consider it as a second-rank tensor denoted by epsilon. That is, epsilon is a linear map between three-dimensional vectors, and the vacuum permittivity epsilon naught times the relative permittivity tensor epsilon transforms the electric field strength E into the electric displacement D. Thus the electric displacement field D is equal to the vacuum permittivity epsilon naught times the contraction of the relative permittivity tensor epsilon of the anisotropic dielectric and the electric field strength E applied to the dielectric. This tensor equation can also be expanded in a given Cartesian basis, providing the component equations of the displacement vector D. As a consequence of the tensor interpretation of the relative permittivity and the electric susceptibility for anisotropic materials, we can also generalize the relationship between them and state that the relative permittivity tensor epsilon is equal to the sum of the second-rank unit tensor I and the electric susceptibility tensor chi-e. Or in a basis expansion, the components epsilon sub ij of the relative permittivity tensor are given by the sum of the Kronecker delta representing the components of the unit tensor, and the components chi sub ij of the electric susceptibility tensor. Since the choice of the Cartesian basis is arbitrary, one can adapt this basis to the symmetries in the structure of the unit cell. Here we can see the hexagonal structure of the alpha quartz crystal projected onto its basal plane. This projections reveals that the crystal has a principal axis of threefold symmetry called C-axis, that is the rotation by 120 degrees or 240 degrees around this axis results in an identical structure. There are other three equivalent two-fold diagonal axes called A-axes that are perpendicular to the C-axis and separated by 120 degrees from each other. We can choose the Cartesian basis vectors so that they form the trigonal system of the crystal, where the xy plane is the plane of isotropy spanned by the diagonal axes, and the z-axis points in the direction of anisotropy determined by the c-axis. For example, the basis vector Ex can point in the direction of the axis A1, where the y-axis lies in the plane of isotropy with the vectors Ex and Ey perpendicular to each other, and the vector Ez points in the direction the c-axis. In the trigonal system of the alpha quartz crystal, the matrix representing the electric susceptibility tensor of the crystal becomes diagonal with the two-fold degenerate eigenvalue denoted by chi-perp, that is the principal value of the susceptibility in the plane of isotropy, and the eigenvalue denoted by chi-parallel, that is the principal value of susceptibility in the direction of anisotropy. By adapting the coordinate system to the symmetries of an anisotropic dielectric, we can therefore reduce the matrix representation of the electric susceptibility of the insulating material to the set of its eigenvalues in the principal axis system of the anisotropy, which simplifies the calculations involving susceptibility. We can also diagonalize the matrix representing the relative permittivity tensor of the alpha quartz crystal in its trigonal system, and use the eigenvalues epsilon perp and epsilon parallel in calculations. We have derived the vector equations describing the relationship between polarization and the external electric field, producing it in both isotropic and anisotropic dielectrics. However, in most cases insulating materials exhibit nonlinear properties, and only a tensorial expansion with respect to the components of the electric field strength can characterize the vectors of the polarization and the displacement due to an external electric field properly. In such a case, the components of the vectors P and D are given by the following infinite sums with a cutoff for a given accuracy, where we show the first and second order terms of the expansions. In the first order terms of the expansions, we recognize the matrix representations of the tensors chi sub ij and epsilon sub ij of rank 2 for electric susceptibility and relative permittivity. Their 3 times 3, that is 9 components, describe the anisotropy of the nonlinear material in the first order. The second order terms contains the third rank tensors chi sub ijk and epsilon sub ijk, represented by 3 times 3 matrices, that is 27 components. These terms are responsible for nonlinear optical effects related to the propagation of electromagnetic waves in matter. The fast increase in the number of parameters as the higher order terms are also taken into account in the expansion, indicates that the description of the behavior of a nonlinear dielectric in an electric field is a challenging task, and we need both experimental data and theoretical models based on the molecular structures of materials. It is also interesting to determine the condition for a non-vanishing volume density of polarization or boundary charges, that is when such charges are present in dielectric materials. For the sake of brevity, we restrict our attention on the behavior of isotropic insulating materials with first-order effects when an electric field is applied to them. In the polarization volume charge density ρP expressed as the negative gradient of the polarization P, we can replace the polarization with the product of the vacuum permittivity epsilon naught and the electric susceptibility chi-e of the isotropic dielectric, times the electric field strength E applied to the medium. Here epsilon naught is a constant, and the divergence of the product is equal to epsilon naught times the sum of the dot product of the vector E and the gradient of chi-e, and chi-e times the divergence of the vector E. Considering the fact that polarization or bound charges are just as much the source of electric field as free charges, Gauss's law can be written in a form where the divergence of the electric field E is equal to the sum of the free and the polarized volume charge densities ρ and ρp over the vacuum permittivity epsilon naught. If we substitute this expression into the right-hand side of the equation for ρp, then we obtain minus epsilon naught times the sum of the directional derivative of chi-e along the vector E and chi-e times ρ, minus chi-e times ρp. By solving this equation for ρp, the polarization volume charge density can be written as -1/1 plus the electric susceptibility chi-e, times the sum of the vacuum permittivity epsilon naught times the directional derivative of chi-e in the direction of the electric field strength E, and chi-e times the charge density ρ. This result tells us that the volume density of polarization charges can differ from zero in two cases. If the insulating material is non-homogeneous where the gradient of the susceptibility is not equal to zero, or the volume density of free charges at a given point in the dielectric differs from zero. If there are no free charges in the dielectric, then the volume density of the bound charges can be reduced to negative epsilon naught over 1 plus chi-e, times the directional derivative of chi-e along the vector E. The figure shows the level curves of the electric susceptibility chi-e in an inhomogeneous dielectric, where the directional derivative is represented by the projection of the gradient vector of chi-e onto the vector E at the point P. This illustrates the fact that polarization charges are present at the point P in the dielectric if the gradient of the electric susceptibility is not perpendicular to the electric field applied to the insulating material.